Hey everybody, welcome back to the fourth and final part of my Homework 1 redo where I'm getting some better camera angles. In part 4, this fourth and final part, I want to vectorize the function from part 3 and then generate a plot of the surface of the helical pipe with the radius I defined before that follows the helical curve defined above. So I think the big question here is what is vectorizing the function, and then how do I need to go through the helical pipe to make it follow the helical curve. So let's start out by talking about vectorize. What is vectorize? Well, fortunately, Jax's documentation is right here to help me out. So I'll say jax.numpy.vectorize or jnp.vectorize, and I need to give it a function written with Jax's Python. I need to give it a signature, and this excluded I can ignore for now. So what even am I trying to do with vectorize? Well, vectorize it's saying it's a wrapper for defining vectorized functions with broadcasting. In the style of NumPy's generalized universal functions, it allows for defining functions that are automatically repeated across any leading dimensions without the implementation of the function needing to be concerned about how to handle higher dimensional inputs. So this is all saying that I'm going to use vectorize to sort of tie together multiple functions. Because right now, if you look at what I have for the surface points, I can only give it one point at a time on the surface. Vectorize is going to let me take this surf function and pass into it a list of values for t and theta. So I already have it programmed out down here. Let me explain through it real quick. I'll define t and theta as lists of values. I will create a vectorized version of surf, giving it a specific signature, and then define that as an array, or take those at some specific points to get an array, and I'll turn that into some x, y, and z values, and I will come down here and plot the x, y, and z values, and my final plot should look something like, actually, I was messing around with this to see what would happen, and I did kind of mess it up real quick. Let me go ahead and correct this. If I just paste these and then paste these, hopefully this will work. And it takes a minute because it's plotting a lot of functions. Okay, so this is sort of the final product we're looking to get, is this helical curve with a cross-sectional radius of 0.5. But let me delete these cells, and let's get into it. So I need to, let's see what I've already done. I've already created the surf function. I need to vectorize the surf function. So I'll maybe go ahead and call this surf vec. So the vectorized version of the surf function is going to be from jnp vectorize. This is what the documentation was talking about. And now I need to give it a function. So I will give it surf as my function, and then I also need to give it a signature. So I'll give it a signature. And what does this signature need to be? Well, essentially the signature is going to tell NumPy, it's going to tell NumPy, I'm giving you a vector of these dimensions, I'm giving you another vector of these dimensions, please return to me a vector of this dimension, or these dimensions. And what I'm going to do is give it a scalar and a scalar, and ask for something with 3 dimensions. And those 3 dimensions are the x, y, and z coordinates of my points. And so if I go back here, I will give it a scalar, so that you use a parentheses as a scalar, give it another scalar, and then I want it to return to me a vector with 3 points on it. Sweet, right? So, yeah, this should hopefully work when I run it. It sure enough does. Let me go ahead and say that the vectorized version of surf, why don't I start out by just giving it 2 random points, doing what I did before, and I'll say when t is equal to 0 and when theta is equal to 0. So I go ahead and run that, and if you look up here at surface point function, it gives me exactly what I had before, but that's because I've just given it 2 individual values. I want to pass into it some arrays of values for it to compare, but as you can see, it does give me the same answer. So how do I get these arrays of values? Well, why don't I go ahead and start off by defining these arrays, right? So I'll go up here, and I'll maybe say that t is jnp.linspace, if I can spell it right, and I'll just do the same t as I did before. So I'll go from 0 to 4 4 pi, j and p pi. I need to use j and p.pi. And then I'll just say I want 32 values just to keep it simple. And then for theta, I want to create a list of values. So similarly, I'm going to use linspace. But I just want one full rotation of a circle, right? Because all I want to do is plot like one full circle rather than doing 2 full rotations. So I'll have it go from 0 radians to 2 times np, j and p. That can really mess you up if you give a numpy function to jax.numpy. And then I want to maybe have 16 points. That's just a number I'm choosing just for the heck of it. So now, when I try to pass no decimal point, t and theta into surf vector, it's going to give me an error. But that error comes from the shapes for the broadcasting arrays not being the same. So that's because, t and theta are arrays of scalar values. So what I want to do is I want to go in here and I'll create some brackets and I'll say I want to take the points of t. I'll take, say, every point of t on the x-axis and then no points on the y-axis. And then if I copy this and then paste it here and do the inverse, so no points on the x-axis and then every point on the y-axis, surf vector should probably not give me an error. Awesome, sweet. So then this is a big list of x, y, and z values. So maybe if I go to the shape here, it'll be a little bit more clear than just trying to look at the array itself. Yeah, so this is saying it's giving me for every 32 values of t, it's giving me 16 theta points, and then each of those points has 3 3 coordinate values, the x, y, and z coordinates. So the problem with this right now is really just the order it's in, right? I don't really love the order of this because the x, y, and z coordinates are at the end. So what I can do is I can go ahead and I can take the transpose, and then I can maybe say that surface vector, I'll go ahead and say points, maybe define an array that way, is the transpose of surface vector. And now when I run that, I won't get any results, but maybe if I just look at the shape, now, yeah, we see the 3 x, y, and z values are at front for every values of theta, for every values of t. So that's pretty sweet. This seems like points is what we want to graph. So let's go ahead and start graphing it. I'll go back up here to definitions and initial curve and steal some code that I wrote in a previous video and come down here. And so I have figure defined as make subplots. I'm going to go through and I'm going to iterate through a range. What range should I iterate through to plot all these various circles and then the lines connecting the circles? Well, let me start off by iterating through t. So I will just do t.size. So for range equivalent to the size of t. On figure, I want to add a 3D scatter plot. And I want to actually, I want to backtrack for a second. And I'm going to say, I'm going to actually break this up a little bit. So now I'll leave it as points, but I'm going to say that x, y, and z are all equal to points. And then if I run that, it should take it. Okay. So then I can say, I want to take x. Well, x is just going to be x, y is just going to be y, and z is just going to be z. But this isn't fully complete yet because I need to take specific values within x, y, and z. And so since I'm iterating, why don't I just say for all values in the sort of first axis for x, I want to take just whatever values I'm iterating for in the y-axis. So then if I go ahead and copy this through and run it, it should run. And let me see what figure looks like now. I'm just trying to plot these points. I think I'm doing in each circle. So this is like all the points on each of the little circles. And sure enough, this is what we get, right? You see a tiny little... Oh, wait, okay. So it's kind of funny. In the middle of my screen, there's like a piece of dust or something on my screen. I don't know what it is. But so I saw that. I thought that was a point in the middle of the graph. But you all couldn't see it because you can't see like the physical things on my screen. Just an interesting little thing that just happened. But as you can see here, looking at all these points, these are the circles that go around the helical curve, like these little orange circles right here. Well, I've just got these right here. So maybe I'll go through and change the line color. So I'll go ahead and define the line color as maybe, what's a good line color? I'll just go orange. Hopefully that works. Hopefully orange is a valid color. It's taking a minute to think. Just keeps thinking. Sweet, now I have all these little orange circles all around the helical curve. So now I could copy this code again. Let's go ahead and do the same thing, but this time for the lines. So I will go through the size of theta, and I will say that I want to do sort of the inverse of what I just did, right? So I'll take for all the sort of first values in the array, or just for the iteration values in the first array, I want to take all the values in the second array. So go ahead and do that. Copy paste, and run. And let's see, give it a few minutes because it is going to need a second to think through and plot all these various points. But sure enough, I got this, and here is a helical curve. And so, yeah, it's a helical curve. It's what I was looking to do. I suppose if, yeah, what do I explain now? Well, this is sort of the end of the project, but I'll summarize everything I did real quick. Sorry, there's something weird going on outside my building. It looks like, I don't even know. I don't know. What is... There's just two guys talking. They're like throwing their arms around. They're not fighting. I don't know if it's a... I think they're laughing now. Okay, I don't know. Anyway, I just got distracted there. Vectorize the function in part 3 and generate a plot of the surface of the helical pipe that has that certain radius at the helical curve defined above. So that's what I just did. So I started out in part 1, and I made a function to calculate the Jacobian of the central helical curve, and then compared it to Jax's version of the Jacobian. Then I generated the tangent and normal vectors using the Frene-Serre formula. And then I created a surface function finder that can find the point at the surface of the helical curve. And then I vectorized that function with a list of values for t and theta. And yeah, that got me through the whole helical curve defined above. And so this all led me to generate this helical curve. I guess if I wanted to play around with it for a second, I could maybe say I want t to have 4 full rotations, so it would be 8 pi. If I run it again, it'll take a minute or two, but eventually it should be able to run. And yeah, okay, so this one looks kind of weird now because I don't have enough values of t and theta. Well, I don't have enough values of t, so maybe I'll set t to have 100 values now. And this is going to take a while to calculate, so I can talk about it for, I guess I'll kind of stall for a second or two while this is generating. But yeah, this is a reshoot of my homework 1, hopefully with this camera angle over here, so that way I wasn't cheating before. I think it's pretty clear based on my work I wasn't cheating, but I don't know, I guess you want some proof or whatever, so yeah. This is the final helical curve. This time it has a lot more rotation, so it's pretty cool. You kind of spin it around. It looks pretty sweet, pretty sick. And yeah, this is the end of my homework 1 refilm. So thank you very much for watching. I hope you have a wonderful day, and bye-bye.